Welcome to a video on common emitter amplifier circuits. So in this video we will actually demonstrate the working of C amplifier practically. So this is a circuit diagram. So we have designed this C amplifier with the value of biasing resistors as 47K. The value of R2 is found to be 6.4K. We are assuming the value of collector resistance as 2.2K, so that approximately I'll get 2.5 volt as the DC voltage here, which will be IC is equal to almost just close to 1 milliampere. And I'm going to do both the responses, time responses and the frequency response. Now let us see the flow chart of this particular C amplifier. So what is the procedure to get a proper output? So now you are asked to connect the circuit diagram as per the design, and you are looking at what is the collector voltage, collector DC voltage, so whether it is half of VCC or not. So this 2.5 corresponds to half of 5, which is half of VCC. If it is close to half of VCC, then you can continue. Suppose if it is too much, suppose if VC is almost very close to 5 volt, or if it is 4.8, 4.9, then you are asked to increase the value of R2 so that you get it close to 2.5. Suppose if the value of if the value of that collector voltage is far less compared to 2.5, if it is like 0.2, 0.3 volts, then you are asked to reduce the value of RC. So this you are supposed to reduce the value of RC. Here if VC is too much, you have to increase the value of R2. So of course, reason for this we'll get it in the other video. So of course, now if VC is too much, if this VC is too much, so I should increase the value of IC. So that can be done using the increasing the value of R2, so that this comes to 2.5, and it is vice versa if VC is very less. Now after you make that equal to 2.5, now you're supposed to apply a appropriate now we will do this practically. So I have a unlock discovery, so I have connected it. Now the value of RC is 2.2K. exactly this is my 2.2K resistance. Where is this? Okay, I have this circuit here. So this is 2.2K I am connecting. So let me just show you this. So this is okay, I have adjusted this to but typically this will be 0.5. you adjust to 1 volt per division. Let this be 0.5. So now you can see it is this is the voltage at collector, which is 3.7, which is not close to 2.5. so what I'll do now is I'll increase the value of R2. You can see now I'll increase it to, now it is 6.1K. let me make it 7.1. you can see it is almost 2.2 volts. So let me slightly make it 6K and then increase the value of R2 in terms of hundreds of ohms. Now you can see I'm increasing now. So now this is close to 2.5K. okay, now this is fine. So now it's almost 7K. So what I can do is I'll make this 100 ohm 0. I'll make it 7K. Now you can see you're almost there. So it is 7K. So it is around 2.4 volt, meaning I could able to achieve this. So I have connected. Now VC is close to 2.5. Suppose, let me see what happens if the value of EC is too much. So now suppose if my value of R2 is very less, so this is what I'll be getting if the value of R2 is too less. Now you can see it's almost 4.7 volt. So then I should increase the value of R2. Suppose if it is something like this. Now you can see this is your VC, which is this condition. So VC is very far less than 2.5. In such case, I should reduce the value of R2. You can see now I'm reducing. Now I just intentionally made the value of R2 to be around 10K. So for that 10K, the VC is very less. So I should adjust this. I should reduce the value of RC so that it comes to close to 2.5. Now our DC conditions are fine. Now let me see what I should do. Now DC conditions are fine. With appropriate setting of the scope, observe the output waveform. So now I should observe the output waveform. Before that, of course I should apply a sine wave of appropriate amplitude and frequency. So let me just go to this wavegen. So if I select this wavegen, by default it is 1 kilohertz. I have to apply a appropriate frequency, which is the midband frequency. Let it be 50 kilohertz. Let me apply a very small amplitude, maybe 10 millivolt. So okay, details of these things we'll just learn in one more video. Why it should be 50 kilohertz, why it should be so less. If I apply this waveform, if I say run, let me go to this scope. Now we can see you are getting the output waveform. So this is your output waveform. Now let me see what is the output peak to peak. I can measure that output peak to peak. Maybe you can just take out this, measure this output peak to peak voltage. Of course we know what is the input peak to peak, so I can stop this. You can see C2 is the output, its peak to peak is okay. You can also observe the frequency of this. Let me observe the frequency of channel 2. You can see now it is 52 kilohertz, which is close to the applied frequency. Now you can see it is, this is okay. Let me compare this. Let me take out this input also. So this is, let me just measure this. Let me just note down the values. Okay, what is my input? V in is 0.01 volt and V naught peak to peak is 0.95 volt. So this is the value that I have, and the value of VC. The value of VC is 2.5 volt. Let me just go here. So these are the values that I obtained. You can see this is my input voltage 0.01, output voltage peak to peak is actually 0.95, and VC is this. So actually these two are AC voltages. This is AC, this is also AC, whereas this is a DC signal. This is okay, let me write it as AC, this is DC signal. You can observe one thing. When you see this in wavegen, this is actually the peak amplitude. You can see this is 10 millivolt. So but here one I am having it as peak, other is peak to peak. So I should make this also into peak to peak so that I can have a proper thing. So is it not 0.2 volt V in peak to peak? So I can find what is the gain of the amplifier. So gain of the amplifier is now given by V naught peak to peak by V in peak to peak. So is it not 0.95 by 0.02? So I can actually find out the gain of this amplifier. It is now 950 millivolt divided by 20 millivolt. Now the gain is 47.5 volt per volt. So this is the gain of the amplifier. So now this is what we have done. So now we have applied the signal, and we are, of course, this is what applied waves, appropriate amplitude frequency, measure the output average voltage and output peak to peak. So that's what is, this is the average voltage, this is peak to peak, this is input peak and its peak to peak. We could able to find the gain of the amplifier. So next is I had to do the frequency response. To do the frequency response, we have the option in AD kit, unlock discovery kit. I had to go for this network, and let me set the frequency as 50 hertz starting frequency, go up to 10 megahertz, let the amplitude be 10 millivolt, and let this top be 50. Now let me run. Maybe to have a proper thicker waveform, you can make this 4. You can see this is my frequency response. What I'll do is I'll stop this now. Okay, this is the frequency response of the circuit. I'll keep it somewhere, stop it now. Now I can actually find out what is the bandwidth and all those things. So I will take few cursors. I'll take one normal, 2 delta, one normal I'll keep it at the midband, and other one I'll keep such that so this delta becomes -3. You can see now this is close to -3 somewhere here. I'm adjusting this. I'm very close to -3. Fine. And you move this also such that it is -3 on the other side. Okay, you just look at this delta y. Okay, this is very close to -3. Okay, now so this is one frequency, this is the other frequency. So this is actually the bandwidth of the. So what we are trying to do now is we are actually trying to obtain the frequency response, which is something like this. Now this is frequency, this is gain in dBs. So this is one midband frequency, and I'm keeping this at 3 dB down. This is again 3 dB down. So this is one frequency, this is the other frequency, and we could able to find out what is this midband gain. So we are finding what is AV midband and two frequencies F1, F2. So this is F1, F2. So we know that F1 is 2 pi R in into Cc. This is 1 over 2 pi R out into C out. So let us know all these things. So let me go back here and find out that. So how much is this? So this is that midband frequency, midband gain, 31.86 dB. So this is my one of the frequency, 280.2 hertz. The other frequency, this is 210 kilohertz, 210 kilohertz. I will just we can actually find out what is this dB in ratio. It is now 10 to the power of 31.86 by 20. It's actually 39.17 volt per volt. So actually in time response I got it as 47. Of course this amount of error is acceptable. So here I got in time response as 47, here I got it as 39.3. So it's not a huge major difference in terms of measurement. So this much is acceptable. So now that's what we have done as per the procedure with appropriate settings in the network. So settings in the networks are these. So you can just have a look at. So start frequency should be very small, the stop frequency should be very large, and make the amplitude appropriate like 10 millivolt. Make the magnitude top as around 50 dB, and you just have 3 cursors, one at the middle, that is 1 normal and 2 delta. So this is the normal one. So put 2 delta so that it is -3 dB down from this. So now you have, these are the two cutoff frequencies, and this is the midband frequency, and this is midband gain. So now what you have to do is next repeat this entire thing by changing the value of RC to 3.3K and 1.5K. So let us do the same thing. So what I'll do is I'll again go for this scope, and I will apply this wavegen. Now let me just again go to scope. Now let me make this resistance to 3.3K. So I just make it 3.3K. Now let me stop this. You can see now when I increase the value of RC from now let me just note the values. So what is the peak voltage? Peak to peak voltage is 1.6. So this is with the value of RC as okay. Now let me have the table. This is RC, VC DC voltage, V0 peak to peak, and we have AV, and we had what AV in dB, and then we got it as AV in volt per volt, and we had F1, we had F2. Okay, let me just write it here like this. Okay, now you can just let us form a table. This is the value of RC. I have VC DC voltage, and I have V0 peak to peak, from which I can find out what is AV. So, and I also found out AV in network, that is frequency response. It was in dB. Then I can find out what is AV in volt per volt using the network, and I have two frequencies F1 and F2, and then let me find out what is GBW. So let me start doing this. So this is 2.2K. The VC was found out to be, okay, 2.5, and I have my output voltage. Of course, input is common, it is 10 millivolt. Output peak to peak was 950. These two are in time response. This was coming out to be 47.5. So AV in dB was 31.86 dB. So let me just write it in a different color. This is 31.6 dB. AV from that was found out to be 39.17. The frequency was F1 was 280 Hertz. This is 280 Hertz. And this was 210 kilohertz. And GBW is actually the product of this into this. So bandwidth, gain into bandwidth. So gain into bandwidth comes out to be, it is 39.17 multiplied by 210 kilohertz. So it comes out to be 8.2422 megahertz. This is 8.222 megahertz. So now this is one more set of readings what I have. This is with the value of 3.3K. The average voltage is 1.4, and the value of output peak to peak is 1.64 volt. This is actually millivolt. And okay, this is 1.64 volt. Let us find out the gain. Let me do the network. Go to network and then run again. So let us again find what are the mid-band gain and the bandwidth. So now let me stop this. Okay, this is 34. Now this is almost close to 3 dB, and this has, now let me adjust this to, this is okay. Now this is fine. Now let me fill this. How much is 34.5 dB. Let us find the gain. This again almost 280 Hertz, but this has changed to 67.6 kilohertz. You can observe one thing. Just clearly observe, as I increase the value of RC, the DC voltage has reduced, whereas the peak to peak has increased. So let us find out what is the gain here. So gain is actually 1.64. Here it is, peak to peak is actually 20 millivolt. So shall I make it 1.64 divided by 20 exponential minus 3. It's now 82. Gain is 82. So this is 10 to the power of 34.5 divided by 20. So this comes out to be 53. Okay, there's a variation. Don't too much worry about this, because we're not doing anything. There is no mistake from our side. So this is the time response gain, this is the frequency response gain. So let us find out what is the gain bandwidth product here. So let us multiply this and this. So now what is 53 into so and so, and 67.6. Can you see it is okay now? let us just take it as, okay, let me just have a let me multiply this with this. So what is this? Now it is 82 into 67.6. Can you see it is 5.54 megahertz. Okay, let us multiply this and this. So gain has increased. Okay, what was the gain here? Let me again go back to this. This is increased and this has reduced. Let me just go back to this and then find out. This is my bandwidth. So bandwidth has 64. Okay, this is what I'm getting now. So I have a bandwidth of 5.54. Let us continue with this, and let me just do it for one more reading. So what does my flowchart says is you have to increase, you have to change the RC to 1.5K. So let me change it to 1.5K and then redo it. Let me change it to 1.5K. Where is this? So I am here. I'll go to scope, I'll run it. I will again go to this and I'll run this. Now this is with again that old, oh just a minute, it's not 1.64, it's actually 1.16. Oh, sorry, this is 1.16. Okay, let me just again redo it. Nothing to worry. So this is what is practical and theoretical thing. So let me stop it now. It is almost there. This is almost there. So now let me just go back to my, this was not actually 1.64, this is 1.16. Now it is, what will be the gain? It is 1.16 divided by 20 exponential minus 3. So gain is 58. Okay, this is 58. You can see 58, 53, they are very close. 58, 53, very close. Now let me find out what is the bandwidth. So what is gain bandwidth product here? So gain bandwidth product was, okay, I actually multiplied 39. In the earlier case, it was 39 into 210. It was 8.2 megahertz. Now it is 53 multiplied by 67.6. It is 3.5. Okay, now it is 3.58 megahertz. So actually, theoretically speaking, this should remain constant. Let us check it out for 1.5K. So this is what the practical value. Let us check it out for a practical value. Sorry, one more RC of 1.5K. So let me just go back here. So what I will do is I will go to scope. I will run this. I will turn on the wave gen. Okay, this one also I will turn on. So let me make this RC to 1.5K. So this is now it is 1.5K. Now let me now stop it. So when I stop this, now it is, let me write the values. So it is now 3.3 volt is the DC, 3.38, and what is the value of V0 peak to peak you have? You have a P0 peak to peak of 870 okay, millivolts. And let me find out what is the network I want to get. Again, do the same thing. Of course, you just follow the procedure properly. Whatever values comes, that we'll see. See, now this is midband gain is around 30 dB, and then you keep this 3 dB down. You can see there's so much variation in the F1 frequency. It's almost there, 280, 330, not a major difference. But you see the other frequency has increased a lot. this bandwidth has increased a lot now. Now it is 3.3. So let me now write the values. So in dBs it is 29.77 dB. Cutoff frequency one is 337 hertz, other one is 2.29 megahertz. 2.29 megahertz. So this is what I have. So let me just show you what is I have rated. Okay, for 1.5K this is this. This is, let me find the ratio of this. This is actually 870 millivolt. Is it not? Okay, 870 millivolt divided by 20 millivolt. Now the gain is reduced to 43.5, and how much will be this? It is 29, 10 to the power of 29.77 divided by 20. It comes out to be, okay, 30. This is my network gain, and if I multiply this into this, so what I have is 30 into 2.29. You can see it is now 60, that is 2.8 megahertz. It is now, okay, I have a bandwidth of, so it is now 68.77 megahertz. So this is the increase in the bandwidth. So let me just find out, go here. Okay, this is, of course it is not coming as per expectation. The gain bandwidth, of course, as the gain reduces, the ultimate thing what we are supposed to observe here is as gain of the amplifier increases, bandwidth should reduce, but gain bandwidth product should remain constant. So here you can see when the gain was okay, let us take the network gains only. So this was 39 and the bandwidth was 210 kilohertz, and then the gain increased to 53. Naturally the bandwidth has reduced to 67 kilohertz, and then this is with the value of RCS 2.2K. This is with 3.3K. With the value of increase in RC, gain is increasing. Now we reduce it to 1.5 kilo ohm. How much is this now? So this is coming out to be 30, and then here the bandwidth has increased to 2.29 megahertz. But here they are not exactly constant. So that's what we want. We'll just look into the, maybe we'll just repeat with one more transistor and then find out. But the procedure is this. But the procedure is, you have to exactly follow this procedure. You can see now, even if it is not matching, it's fine. But you can see conceptually, as the gain increases, you can see gain increased, bandwidth reduced. Gain has reduced from 39 to 30. The bandwidth has increased here. Bandwidth has increased here from 210 to so and so. So let me just redo this for 2. One important thing that you can notice here is, let me also find the value of IC. Let me also find the value of IC here. So that will tell me how does your collector current will change. So IC in this case is, it's actually what is IC value given by. So IC is given by VCC minus VC by RC. So this is the expression for IC. So let me find out how much is that. Is it 5 minus 2.5 divided by 2.2K. So it is 1.13. It's actually in terms of milliamperes. For the second one it is 5 minus 1.4 divided by it's actually 3.3K. So 1 second, it is 5 minus 1.4 divided by 3.3. It's actually, you can see it's almost 1.09 milliampere. So current is almost remaining constant. Let me check out for this. Can you see it is now 5 minus, let me just open the parenthesis, 5 minus 3.38 divided by 1.5K. Can you see it is 1.08? So So if you can notice this, the IC is remaining constant. So what I mean to say here is the MOSFET or the BJT is operating in the active region of its characteristics. So this is the value of VCE or VC, this is the value of IC. If you change the value of RC, first VC was 2.5 volt. The current was almost close to 1.13 milliampere. When you increase the value of RC to 3.3K, so this has reduced to 1.4, it came here, but you can see the IC is almost remaining constant. Now when you reduce the value of RC to 1.5K, that has gone to some 3.38, but you can see current still remains same. So as long as you are operating in this active region, so this is active region in BJT, which is analogous to saturation region in MOSFET. So as long as BJT is operating in active region, this current remains constant even if you change the resistance to a smaller value or larger value, provided MOSFET or the BJT should be in the active region. So this is one typical readings you will get it while performing a C amplifier. Hope you can able to now relate it to the experiment that you have done in your lab. Thank you.